Welcome to Statistics 101, where we learn statistics one bit at a time in under 10 minutes. In this episode, I want to talk with you about expectation values for discrete random variables. So let's start. One of the first use cases of statistics was of course gambling, since gambling consists out of three elements, right? We have a consideration to make, a chance to take, and a given result. Given that gambling has been around for almost as long as humans have, the ability to analyze it using statistics was a significant achievement. You probably also heard about those players who use card counting and blackjack, that are using a mathematical strategy to keep track of the relative proportion of high cards to low cards remaining in the deck. By doing so, they can estimate the likelihood of receiving a high card on the next hand, which influences their betting decisions. These players typically aim to achieve a positive expectation value, which means that they expect to win more money than they lose over a long run. And today, we are gonna learn more about the expectation value. So as a quick motivation, let us go through the following gambling scenario, where you got a dealer that throws a coin. When this coin lands on tails, you will win $2, and if it lands on heads, you will lose $1. But the coin is unfair. The probability of getting heads is 0.7 and tails 0.3. The dealer asks you, do you wanna play? Before answering this question, we will have to learn what an expectation value is. So let's start with the following definition. Let x be a discrete random variable with support Rx and probability mass function Px of x. Then the expectation value can be defined as P of x, which is equal, and then we sum over all realizations over x times Px of x. And we also want to have an additional requirement, that is, we sum over realizations over the absolute value of x times the Px of x, and this should be smaller than infinity. And this is also called absolute summability. And this is a really desirable property because it helps us in many situations. For example, one such a situation could be that we are summing over an infinite large set of realizations. And normally in those kind of summations, the order in which we sum up the terms matters. And this would be bad, because then the expectation value wouldn't be defined, right? Because if you switch two terms, you would get a different result. But if we require absolute summability, then the ordering doesn't matter. And then we have a well-defined expectation value. There are some additional properties and characteristics which come with absolute summability, but I won't dive deeper into this in this episode. So let's talk through an example in order to better understand this definition. Suppose you got 4 cards. 3 of them are red and 1 is green. But those cards are turned down and we cannot see the color. If we tip on the green card, we win $2. Otherwise, we will lose $1. We can start out by writing our probability mass function. Our probability mass function is 1 over 4 if x is equal to 2. 3 over 4 if x is equal to -1, and 0 otherwise. So the support contains 2 elements, -1 and 2. With those information, we can already compute the expectation value. We just have to multiply each element in the support, which is the price that we get, with the probability of obtaining that price. The result is -$0.25. So on average, we will lose money and we should stay away from this game, right? An expectation value has many interesting properties. So let's go through some of them, which are quite important. The first property is this one. Consider n realizations where each realization can occur with probability 1 over n. Then the expectation value is given by this expression, which we can rewrite to the following form. And this gives us arithmetic mean. Essentially, the arithmetic mean is a special case of expectation value with equal weighting of the realizations. The second property is about an expectation value being greater or equal to 0. because if a random variable is greater or equal to 0, then the expectation value of x will be also greater or equal to 0, since the probability must lie in the interval from 0 to 1, and xi is also greater or equal to 0. And since in the expectation value we are summing over the terms xi times pi, and since those are equal or greater to 0, the sum will be, of course, also greater or equal to 0. Another interesting property is the third one, where the sum of an expectation value of a random variable x and the expectation value of a random variable y is equal to the expectation value of the sum of those random variables. This is the case since we can rewrite the left-hand side of this equation to the following expression. Essentially, what we have to do is we just have to plug in our random variables, right? So we have the expectation value of x plus y, and this is the same as we are summing over xi plus yi, and the whole expression times pi, right? And what we can do is we can then multiply pi inside of this bracket, and what we then can do is we can just split the sum between those two terms, and we will arrive at our expression we want, that the expectation value of x plus y is equal to expectation value of x plus the expectation value of y. Let's talk through an example to see if what this implies. So let's say we have a random variable x and y. X is minus 1 if x is equal to 0, and 1 if x is equal to 1. Y is 2 if y is equal to 0, and 0 if y is equal to 1. And the probability for each realization is equal to 1/2. We can combine those two random variables into z by summing over the realizations. Z is then 1 if z is equal to 0, and 1 if z is equal to 1. The expectation value for x is equal to 0, and the expectation value for y is equal to 1. And the expectation value of z is also equal to 1. And indeed, the expectation value of x plus the expectation value of y is equal to the expectation value of z. The last property which we should know about is this one, where we can show that one is able to extract the scaling parameter a and the shifting parameter b out of expectation value. This can be shown in the following way. So we just have to write out our expectation value formula again, where we are summing over a times xi plus b and the whole expression times pi, right? What we then can do, we can again multiply pi inside of our bracket and then split the sum on those two terms. And we note that the sum over b times pi, we can extract b out of the sum, and the sum over pi over all possible values is of course 1. And so this is equal to b. So we have, the whole expression is equal to a times the sum over xi times pi plus b, and this is equal to a times and the expectation value of x plus b, right? So indeed, this is what we wanted. So let's go through another example, where in this example we have a random variable x, which is minus 1 if x is equal to 0 and 1 if x is equal to 1. And the probability for getting minus 1 is 2/3, and the probability for getting 1 is 1/3. And the scaling parameter is 0.5 and the shifting parameter is 0.25, for example. And what we can do is we can calculate, for example, the expectation value of f from x, which is equal to minus 1/3. And when we can just multiply that by our scaling parameter and adding our shifting parameter, and what we get is 1/12. And now we can do the same calculation, but this time we plug in a times x plus b into our expectation formula. And we can do this a little bit more lengthy computation, but we arrive at the same result, which is 1/12. So we again see that this really matches. Now it is your time to shine. Compute the expectation value for the scenario that we talked at the beginning and answer the following question. Would you join the dealer in his game? Click on pause on this video and try to solve it on your own. I'll wait 5 seconds and show the solution afterwards. So this is the solution for our beginning scenario where we would win $2 if our coin would land on tails and lose $1 if it would land on heads. But on heads, it would land with a probability with 0.7 and on tails with 0.3. And the expectation value is 2 times 0.3 minus 0.7 times 1, which is equal to minus 0.1. And thus we would lose money on average and we shouldn't play. So that's it for this episode. I hope you like these mini tutorials about statistics and that we see each other in the next episode. See you then.